Okay, let's put this definition of derivative to use here. Our definition derivative, in this case, typically it's done with f of x. It's shown that way, but it is the limit as h, some value h, approaches 0 of, I'm going to use g's, g of x plus h minus g of plain old x all on h. Now, this point, this problem number 10 is really intending on us going directly to use this point, and I'm not going to do that. I'm going to find the slope formula of this guy by running this through our definition of derivative. I'm going to find just the general form and then come back to deal with the point 4 1/2. One thing we should note is that 4 1/2 is a solution point for g of x. When we put in 4, we get 1 on 4 minus 2, or 1 on 2. So 4 1/2 is on the graph, and we want to know what the slope of the curve is when x is 4. So I want to put g of x into g, and g is a factory that takes things, subtracts 2 from them, and puts them under 1. So I'm going to take x plus h, subtract 2 from it, and put it under 1. Then I'm going to subtract from that plain old g of x, 1 on x minus 2, and all of that goes on h. So we create a bit of a mess. Of course, we're looking for the limit as h approaches 0. Okay, so if we plug 0 in for h right now, you notice we would get 1 on x minus 2 minus 1 on x minus 2, 0 in the numerator, 0 in the denominator. So we have to do some manipulation. So the first thing I might think of doing here is manipulating this by getting rid of the compound fractions. And I would do that this way. I would say, in my compound fraction, my two denominators contain factors of x plus h minus 2 and plain old x minus 2. And if I multiply the top and bottom by that, I'm not changing the value, just the form. So, times x plus h minus 2 times x minus 2. Then in the numerator, when I take this whole package and distribute it to my first term, the x plus h minus 2 factor cancels, and I just get a 1 times x minus 2. When I distribute the whole package to the second term, to the minus 1, the x minus 2's cancel, and I'm left with just the factor x plus h minus 2. And I'm not distributing or foiling anything in the denominator. You'll see why shortly. I get h times x plus h minus 2 times x minus 2. Okay, my next step should be really revealing. If you do the next step right on definition of derivative or finding slope formulas, everything in the numerator that does not have an h in it should cancel. For instance, I get an x, but I subtract an x. I've got a minus 2, but later I'm going to add a 2. All I really end up with in the next step is this term, negative h on h times x plus h minus 2 times x minus 2. And you may be thinking, well, what good is that if we want the limit as h approaches 0? Because if I put in 0 now, I quickly see the numerator becomes 0. The denominator has a factor of h, so that's 0 times. I still have 0 over 0, but of course, I can cancel an h now. I would end up with h canceling the h, leaving me with just negative 1 in the numerator. Now, direct substitution, I put 0 in for h. The numerator is negative 1. The denominator, 0 in for h, and I get x minus 2 on x minus 2, or x minus 2 squared. And this is so important to this original function g that we could give this 3 pretty good names. We could call it the slope formula, we could call it the derivative, and we could notate it by calling it g prime x. And we'd say the derivative of, or the slope formula of x is negative 1 on x minus 2 squared. So that's our slope at any given general problem, any point x. But what I'm looking for is what is the slope when x is 4? I'm looking for g prime of 4. But g prime is a factory that takes things, subtracts 2, squares them, and puts them underneath negative 1. So I get negative 1 on 4 minus 2 squared, or our slope at that point is negative 1/4. And if you came away from that, and that's the first of these you looked at, and you came away from that feeling like, you know what, I get it maybe 25%, but I'm going to have to get some practice and see some more, well, you're going to get some practice and see some more of these.